So this week we're going to talk about LU factorization, or matrix factorization. This is really just an extension of Gauss elimination, so we're going to revisit our row operations. It just so happens that this process is very algorithmic, which means it's the same steps every single time, so don't change it. Okay, before we get into that process though, we need to talk about elementary matrices. So elementary matrices are just the identity matrix, where we perform one row operation on the identity matrix. So there's three types of row operations, which means there are three types of elementary matrices corresponding to the row operations. So for example, over here, if I take this matrix, this identity matrix, and I swap these first two rows, I will end up with this. Which this here is an elementary matrix. It's specifically called a permutation matrix. We'll get to that later. But that's an elementary matrix because I performed one row operation. For this one, let's say I went ahead and I said row 2 equals 5 row 2. I would get this matrix, which once again, this is also an elementary matrix because I performed one row operation on identity. And then for this last one, let's say I took row 3 and I replaced row 3 by adding 3 row 2. My matrix is going to look like this. Row 3 now becomes 0, 3, 1, where I have this 3 that shows up in a non-zero location. Okay. And it turns out that when we have an elementary matrix, the determinant is non-zero, which means the inverse exists, and that inverse is the elementary matrix of the same type. So it's very similar to whatever it originally was. And that comes into play in how LU factorization is derived. So let's go ahead and focus on this last type here. This last type here is called an elimination matrix. And we'll see those a lot when it comes to LU factorization. And you'll notice that for an elimination matrix, we use row operation 3, which is defined strictly as row x equals row x plus some multiple of row y. And so this is strictly row operation 3, where there's a 1 here, so the row we're replacing is not multiplied by a factor. So keep that in mind. And what happens is EIJ is what we'll call it. EIJ has an extra non-zero entry L in the IJ position. So what that means is we notice there's a 3 here in the 3, 2 position. Okay. The 3 and the 2 here come from the 3 and the 2 here. I replaced row 3, so it shows up in row 3, using row 2, so it shows up in column 2. Okay. And this 3 here is exactly the same number I multiplied my row 2 by. Okay, so given a row operation, we can construct the elimination matrix. Because we're going to use the rows. The rows are placed as the column our multiplier shows up in, or as the row our multiplier shows up in, and the row we used is the column our multiplier shows up in, and the multiplier here is in that position. So that's what that means. And then it turns out if we take this elimination matrix and we multiply it by A, let's say I do E, this is going to be E32, and I multiply it by some A matrix, it actually performs that row operation for me. So it's going to replace row 3 in A by adding row 3, or by adding some multiple of row 2. So it does this row operation on A. So my result is A with that 0, or with that elimination step, right there in that 3, 2 position. Another thing about these matrices, another property of these matrices, is that the inverse of the elimination matrix is the same as the elimination matrix itself with the sign change. So the inverse here, E32 inverse, is going to be the exact same thing with a negative now on the 3. So notice they're exactly the same except for my 3, my multiplier, has a negative sign. So I change the sign of my multiplier. And once again, that goes into how LU factorization is derived, which we will talk about in our next video.